Assalamualaikum warahmatullahi wabarakatuh. Today we are going to present pair work for MAT652 algebraic structure. This project is prepared for CSD bin Masar. Our group members consists of two, which is Muhammad Luqman Amin bin Muhammad Hidayat from N4 CS2495B2 and Muhammad AKMAL bin Yahya from N4 CS2495B3. Firstly, we start with questions. So we have two questions. Question 1 related to Theorem 1, while question 2 related to Theorem 3. Theorem 1. Let A be a non-empty set, and let S subset of A be the collection of all permutations of A. Then S subset of A is a group under permutation multiplication. So firstly, we prove by closure. By lemma, we know that the product of two permutations of set A is a permutation of set A. So S subset of A is closed under multiplication. Next, we prove by associativity. We now show that SA is a group, since permutations multiplication is defined as function composition, and function composition is associative. So S subset of A satisfies property of G of the definition of a group. Next, we prove by identity. Identity permutation is iota defined as iota A equal to A for all small a element of capital A, since sigma I equal to iota sigma equal to sigma sigma for all sigma element of subset of A, as subset of A. So G2 is satisfied. Then finally, we prove by inverse. For sigma, finally we prove by inverse. For sigma element of S subset of A, define sigma prime on A as sigma prime A prime equal to A if and only if sigma A equal to A prime for each A element of A. Since sigma is 1 to 1 and onto A, sigma prime is well defined 1 to 1 and onto. For each small a element of capital A, we have iota A equal to sigma prime A prime equal to sigma prime sigma A equal to sigma prime sigma A, and iota A prime equal to A prime equal to sigma A equal to sigma sigma prime A prime equal to sigma sigma prime A prime. And so sigma prime sigma equal to sigma sigma prime equal to iota. That is, sigma prime is the inverse of sigma. And for information, we denote sigma prime equal to sigma inverse. So basically, sigma prime is sigma inverse. So G3 is satisfied. So for now, for the example question, permutations A and B are in S subset of 7 as following. So we've given A and B, so we need to find A inverse and B inverse. Hence, evaluate A, B inverse, A inverse, and write the answer in cycle notation. To find A inverse, first we need to write down from 1 to 6, 1, 2, 3, 4, 5, 6, 7. 1 maps to 7, 2 maps to 6, or 2 maps to 6. 4 maps to 1, 5 maps to 5, 6 maps to 2, and 7 maps to 3. Same goes to B inverse. Next, we need to find A, B inverse, and A inverse. And from here, we need to look from right to the left. 1 maps to 7 and 1 maps to 7 and 7 maps to 7. And then 7 maps to 1. So 1 maps to 1. 2 maps to 6, and then 6 maps to 5, and 5 maps to 5. So 2 maps to 5. 3 maps to 4, 4 maps to 1, and then 1 maps to 4. So 2 maps to 4. So we repeat the same process, we get the answer, the rest of the answers. And we need to come up with the disjoint cycle notation. As you can see, 1 map to 1. So we have the first cycle, and then C2. 2 is mapped to 5, and then 5 is mapped to 7. Then 7 maps to 2, and then we have a second cycle. Finally, we look at 3 maps to 4, then 4 maps to 3, and then we have the third cycle. Since 1 maps to 1, so 1 maps to itself. So we only have the final answer to 2 cycle, which is 257 and 34.
Assalamualaikum. My name is Muhammad LUQMAN bin Muhammad HIDAYAT. So let's proceed to question 2 using theorem 3. So let phi is G maps onto G prime be a homomorphism of groups. Let H equals to kernel of phi and A element of G. Then phi prime phi of A equals to AH equal to HA. In particular, the left and right cosets of kernel of phi are. To prove the theorem, recall that phi inverse phi of A equals to x element of G. Phi of x equals to phi of A. Now, x element of phi inverse phi of A biconditional to phi of x equals to phi of A biconditional to phi of A inverse x equals to phi of A inverse phi of x equals to identity. Biconditional to A inverse x, element of kernel of phi equals to h biconditional to x, element of. So, phi inverse phi of A be a subset of AH and AH be a subset of phi inverse phi of A. So, phi inverse phi of A equals to AH. Similarly, phi inverse phi of A equals to HA. So we got the theorem has been proved. Next, we proceed to the example question. So from the question, we let phi is G maps onto G prime be a homomorphism of groups. The kernel of phi denoted by kernel of phi is phi inverse identity equals to x element of G such that phi of x equals to identity. Given a homomorphism, phi is integer maps onto group of integer modulo 56 such that phi of 1 equals to 14. Find the kernel of phi and phi of 60. Next, we proceed for the solution. So from the question, we get phi is integer maps onto group of integer modulo 56 and phi of 1 equals to 14. And for the formula, phi is integer maps onto the group of integer modulo n, universal kernel of phi equals to order z. Then order equals to n over GCD an equals to 56 over GCD 1456. Since the dihedral modulo 14 and 56 has 14, we substitute GCD 1456 with 14 and we get 56 over 14, which is equals to 4. Hence, kernel of phi equals to 4z. Next, phi of 63 equals to phi of 60 plus 3, which is equals to phi of 60 plus addition modulo 56 with phi of 3 equals to I plus addition modulo 56 plus phi of 1 plus addition modulo 56 with phi of 1 plus addition modulo 56 with phi of 1, and we get 14 plus addition modulo 56 with 14 plus addition modulo 56 with 14, and we got phi of 63 equals to 14.